Let's look at number 30, integral from a to a plus 2 pi sine of t dt, where a is any real number. Let's just do it blindly by algebra first, and then we'll go graph it and see what's going on. So what the antiderivative of sine is what? Cosine, negative cosine, from a to a plus 2 pi. We could put the bracket outside or inside the negative, either way is fine. So then we get, when we plug this in, cosine of a plus 2 pi minus cosine of a. And at first it seems like, well, okay, we're just kind of stuck. What can we do with that? Can we say that cosine of a plus 2 pi is cosine of a plus cosine of 2 pi? Well, let's think about that. Is cosine of a plus 2 pi equal to cosine of a plus cosine of 2 pi? And it turns out that is not true. You can basically never take the sine or cosine of a sum and just write it as the sine or cosine of the individual terms. So we cannot do that. What can we do? We can say that a plus 2 pi is 2 pi later on the timeline, but cosine has a wavelength of 2 pi, so cosine of a plus 2 pi is the same y value, just moved over by 2 pi. So this whole term is just cosine of a. So I'm not saying you can always get rid of the plus whatever. I'm just saying because it's 2 pi and we don't have a frequency multiplier here, we're going one full wavelength into the future, and so we get the same y value. Minus cosine of a, and we have a minus sign out there. And so altogether we get minus 0, or just 0. So what's going on there? Let's look at Desmos. And in Desmos we usually have an a and a b, a start and a stop. So we're going to say b equals a plus 2 pi. And then we'll make a slider for a. And we'll slide it around and see what happens. All right, here we are with f of x equals sine x and b equals a plus 2 pi. So we're saying what's the integral from a to a plus 2 pi? And right now, what does it look like that integral is? It looks like this bump cancels out that bump, or vice versa, and you get 0. And what if I slide a over this way? Then does it look like the bumps cancel out again? Or what if a didn't even go that far? Does it look like the negative part of this bump, which is negative, cancels out the total positive part here? And what if I do this? And what if I do this? Does it look like it's always going to just cancel out? So you could say the integral of a sine wave over one full wavelength is always 0 no matter where you start on the sine wave. What if you started halfway up? Then that would pretty much be like a cosine, right? Starting a lot high and moving downward. So you could also say the integral of a cosine wave over any full wavelength is 0, as long as it's a pure cosine wave, not like cosine squared or sine squared. So that actually ends up being pretty handy in some parts of Calc 2 especially, but it's also a useful thing to know in general. Let's switch back to paper and pencil and look at a related problem. So there's another problem where it says, what's the integral negative 1 to 1 x to the n dx for n being an odd integer? That seems kind of vague to begin with, but we can just try different odd integers. So let's try n equals 1. So we're saying integral negative 1 to 1 x to the 1 dx. And we should plot that. Here's x to the 1, that's just y equals x. And we're going from negative 1 to 1. And what does it look like that integral is equal to? Well, it looks like we've got some negative area here and some positive area here. And looks like they cancel out, so the net area is equal to 0. Let's try n equals 3. That's another odd integer. How about, let's see, negative 1 to 1, x cubed dx. What does that look like? Something like this. And does that look like this area here is going to cancel out that area? Yep, so the net area is 0. N equals 5 looks pretty much like n equals 3 when you do a by hand sketch. It's symmetric around the axis, so the net area is still 0. That's graphically, but let's try it numerically, actually doing the integral. So we'll go negative 1 to 1 x to the n dx. What's the integral of x to the n? It's x to the n plus 1, 1 over n plus 1 from negative 1 to 1. So we'll put the n plus 1 out here, and we're going to substitute 1 to the n plus 1 minus 1 to the n plus 1. Now we have to think about what's going on here. Got 1 over n plus 1 there. What is 1 to the anything? 1 to the anything, that's just a simple constant plus 1 is 1. And then what's negative 1 to the n plus 1? Well, n here was odd, and odd plus 1 is even. So what's negative 1 to the even power? Put a big question mark there. That's like negative 1 squared, or negative 1 to the 4th, etc. We're going to be multiplying it by itself an even number of times, and so all the negatives will cancel, and so we'll get a positive 1. And what's 1 minus positive 1? It's 0. So altogether we get 0. So what this is hinting at is this function is symmetric around the origin. And if you're integrating symmetric around the origin function symmetrically from left negative something to positive that same thing, you could just say it's 0. So the integral of a symmetric around the origin function using like minus a to plus a, so minus a to plus a is 0, the areas just end up canceling out. That actually comes in really handy in some parts of Calc 2 when you've got a function that actually looks really nasty to integrate. You'd have to use U substitution, maybe even integration by parts, but then you notice it's symmetric around the origin, and it's from negative something to positive that thing, and you can just say, oh, this whole integral is 0. Makes life a lot nicer there. Let's do a related thing. How about negative 1 to 1 x to the n dx, where n is an even integer. Oh, we have to say positive here too. Actually, we should think about that. Do we really need these integers to be positive, or does it keep working with negatives? That's an interesting story, I think. So we can try n equals 2. We'll get parabola like that. At n equals 4, we get something like a parabola, but much flatter at the origin. So what can we do here? It's symmetric left-right, not through the origin. So it's symmetric across the y-axis. Not through the origin. I wrote symmetric across the y-axis, but not through the origin. Are there any functions that are symmetric across the y-axis and also symmetric through the origin? That's a fun little puzzle. So whatever the area is on the left half, is going to be the same as the area on the right half because we're integrating symmetrically from negative something to positive that same thing. So we could say that whatever area was over here, we can just multiply it by 2 to get the area that was over here as well. So we could say it's 2 times integral 0 to 1 x to the n dx. And we still have to do the integral. The integral's not hard. We actually did it up here. But the point is, would you rather plug in -1 or would you rather plug in 0? I would rather plug in 0. It tends to make things a lot nicer. So it's easier to do usually because plugging in 0 is nicer than plugging in -1. You don't have to think about, like, do I put the parentheses around the negative or not? So you'll end up plugging in 0 instead of -1. So if you notice something is symmetric across the y-axis, and you're integrating symmetrically from negative something to positive that same thing, then you can use symmetry and say, oh, I'm just going to do this from 0 to whatever upper limit and multiply by 2, and that makes the final plugging in easier. You might remember that things across that are symmetric across the x-axis are called even functions, and things that are symmetric across the origin are called odd functions, and that's because the even powers of x have this symmetry and the odd powers of x have that symmetry. Let's do another quick problem or two to highlight a trouble spot. Let's do, and I know we just did something like this, let's do integral -1 to 1 of x cubed dx. So we'll graph it first. I know we just did this, but let's do it out, and I'll show the right way and the way that some people do it that ends up not leading to what we want. Let's say this is 1/4 x to the 4th -1 to 1. And then, let's see, some people would say this is 1/4 of 1 to the 4 minus 1 to the 4. Other people would say this is 1/4 1 to the 4 minus 1 to the 4, like that. Which one of those looks more correct? Or do you think they're the same thing? Well, you're probably guessing, oh, if with extra parentheses there, that's probably safer, and that's what we should do, and that's right. So we'll put a yes there, and a nope there. That would equal 1/4, 1 to the 4 is 1, minus, and the 1 to the 4 happens before the minus sign because of order of operations, and so we still have a minus there. And what is 1 minus -1? That's 2, so we'd have 1/4 times 2. This one would be 1/4, 1 minus, and -1 to the 4th is +1, so we get 1/4 times 0, and we know from the symmetry the answer should be 0. So you got to watch out with your parentheses there. Let's do something similar. Let's do integral 2 to 5 7x minus 9 dx. So go ahead and take the antiderivative as usual. So we'll say that's 7x squared minus 9x from 2 to 5. And then we'll plug in the 5 and stuff. So we'll do 7 times 5 squared minus 9 times 5 minus 7 times 2 squared minus 9 times 2. What do you think of that? Well, the trouble is that I need to subtract everything I get when I'm plugging in 2, and what I get when I plug in 2 is 7 times 2 squared minus 9 times 2, and I need to protect this whole thing with parentheses, otherwise I'm going to have trouble. This minus would end up not canceling that if I didn't have the parentheses. So that's another common trouble spot. Let's do one more. How about the integral from 3 to 4 7x minus 9 squared dx? So go ahead and take the antiderivative. Did anyone say that this is 1/3 7x minus 9 cubed? From 3 to 4. It seems like a certainly understandable thing to do, but if you check it by taking the derivative, you end up with a chain rule. So I'm just going to check the antiderivative, not the plugging in 3 and 4. So we'd get 1/3 7x minus 9 cubed prime. So that's 1/3 times 3, 7x minus 9 times squared times 7x minus 9 prime. All that cancels, so you just get a 1 out there. 7x minus 9 squared times 7, but I didn't have a times 7 in the original. So you can only use the power rule when you have a just plain x or t or theta or something to a power, not a function of x or t or theta. So when it's a plain variable to a constant power, not a function of a variable. To a constant power. For this function of a variable to a constant power, for that you need chapter 6.1 U substitution, and we'll get there pretty soon.